Okay, good morning, Astronomy 1010. Welcome to our Wednesday class. Couple of announcements. We have a lecture today on energy, atoms, and aspects of light. We'll be doing a homework. I have a meeting with the Vice President at 3 p.m. today, so I have to finish our homework before 3 o'clock, okay? I think that'll be fine today. Today is one of the shorter homeworks, so we should be able to get it done well before 2 hours are up. But I just wanted to mention that now so that if I have to rush us at the end, you'll understand why. I'm going to hide the trolls here so I can focus on the people who want to look at me and talk to me. Today, hello Juan, we're going to begin by talking about energy. I think we ended up at our last lecture doing tidal forces. Is that right? That's how is that what you see in your notes? Yeah, okay, Andrew, thank you. All right, so last time we learned about tidal forces, we learned about momentum, and energy is another abstract property of physics that is similar to momentum in that it's an abstract quantity that's difficult to think about at first. But if you train yourself and you allow yourself to think in terms of energy, it gives you deep insight into physical systems, and it kind of makes you a sort of wizard of science. Speaking of wizards of science, they've been announcing the Nobel Prizes for physics yesterday and chemistry today. The Nobel Prize in physics went to 3 researchers who study supermassive black holes. Andrea Getz was the American, Roger Penrose was the theorist, and Richard Engel, I believe. Richard Engel was the third one. In any case, they 2 of them are observationalists who discovered evidence for the fact that there's a supermassive black hole in the center of the Milky Way galaxy. So that's kind of cool to see Nobel Physics Prize going out to some astronomers, you know? Everybody loves supermassive black holes too, so. Okay, anyways, make sure you go and check that out. You can read about it in the Washington Post or whatever on your tea break if you'd like. Okay, so let's learn about energy. That's how we're going to start off today. If you think about it, energy is a term that comes up all the time in everyday language, like, I have a more energy efficient car. I've got a more energy efficient house. Or, oh crap, I'm out of energy. But what is this energy that people talk about? Most people think of it as like the blue glow that's around Superman. But there is a technical definition to energy, a definition which is so subtle and so sublime that you might not even understand what it means the first time around. Let me get out my Logitech camera for focusing issues. Okay, so the fundamental definition of energy is actually kind of abstract. It goes like this. Energy is a force multiplied by a distance, okay? And although this is the true, most generalized definition of energy, at your stage of development, this definition is not very helpful. It's sort of like you already have to understand energy to understand what this means. So let me start by telling you a few bullet points about energy that'll help to organize your thoughts. The first thing that's interesting about energy is it's an abstract quantity that takes various forms. This is one of its key signatures. So to get a little cheesy with you, if you've ever watched a science fiction movie or a fantasy movie in which there's an alien that can shapeshift and take these different forms, energy is very much like that. It can constantly rear its head in different configurations, and you'll be surprised, oh, that's another form of energy. Many of these forms of energy fall under one of 2 general categories. There are potential energies, and there are types of kinetic energies. These are the sort of two general categories. Potential energies are usually energies that are stored. Kinetic energies are usually associated with the motion of moving objects. And there's even a third form of energy, which is light. Light, I'd say, is kind of a pure form of energy that is neither potential or kinetic, but has aspects of both. So energy can be very, and there are other types of energy that I may not even be addressing right here. Here's yet another issue about energy that's extremely important. Like I told you on Monday about momentum, energy is a conserved quantity. Energy can neither be created nor destroyed, but the total energy in a system, whether the system is a box or an oven or the whole damn universe, the total energy in a system is always constant. You may have heard of the conservation of energy. That's what I'm talking about here. The fact that energy is constant gives it powers similar to that of momentum. You can figure out what's going to happen when systems interact with each other. By knowing the total energy of a system is constant, you can predict how it will evolve over time. So the payoff is it's a more abstract quantity to think about than distance or mass, but it's ultimately better at giving you insight into how things work. I'd like to talk about the units of energy, but first I'd like to get this a little more tangible, and I'd like to zoom in on potential energy and just kind of introduce you to a single form of energy as a good way to start by thinking about things. Let me let you catch up to these notes because I'm going to need the whole board for the next little bit.
Oh, this medical place is dope. It buys cars, and there's heart scans, cancer, and blood. It's fucking
Hey,
sick.
whoever's watching TV, you should probably mute yourself so I can't hear that. Thanks. Okay, I'm going to erase them. Andrew, how you doing?
I'm all done.
Thanks.
No problem.
All right, so let me start by introducing a type of energy called gravitational potential energy. Introducing gravitational potential energy. And if I had to define it, I would say it's the energy stored in a gravitational field, whatever the hell that means. Usually what it means is this. You have the ground on Earth, okay? So this is the ground. And you start off with some type of a test mass. Like, for instance, an ideal test mass would be this 1 kilogram reference mass that I have here. You'll notice it says 1,000 grams right there, okay? So I stole this from the physics lab, and I brought this home with me. I thought it might be useful. And we can actually create some energy right here in this room by putting it on the ground and lifting it up. So this morning, which was not that long ago, I had myself some maple syrup oatmeal, and I gave my muscles some energy, okay? And so once this thing is on the ground, I can use some of my muscle energy and convert it into gravitational potential energy by lifting it up off the ground and holding it up over my head. I don't know, a height that's probably about 2 meters or so. This is 1 meter and this is 2 meters. So there I go. I'm holding it 2 meters above the ground, okay? And now I've created some gravitational potential energy because I've fought against the will of gravity, which wants to pin this to the ground. So here is my reference mass, and I'm holding it some height above the ground, we define potential energy in the following way. Potential energy is the mass times little g times the height that I've lifted off the ground. Class, can you remind us what little g is again? Because I get forgetful sometimes and I can't remember things. What is little g?
Gravity?
Well, that's not good enough. Gravity is
gravity.
okay, but it's not Earth's gravity, it's a more specific, Frank,
Ground.
can you tell me what
Grams?
it is?
What was that?
Can you tell me what the number is?
The number?
Yeah. See, Frank, by saying Earth's gravity, you're close, but you've got to be more specific than that. Because if you say Earth's gravity, I could think you mean the force of Earth's gravity. And little g is not a force. You see what I mean?
Yeah.
It's definitely
I don't know
related
what
to
you mean. I don't know what you mean by when you want numbers.
well, little g has a value. Someone out there has to remember what little g is. Otherwise, look it up in your notes. Do some research.
10, right? Or negative 10
It's 10, but what are the units? 10 isn't good enough.
meters per
Grams?
second squared.
Thank you. What kind of a
Oh.
quantity is that, meters per second squared?
Acceleration.
That's right. Frank, this is who was I just talking to there? I lost track.
Noah.
Sorry?
Noah?
Oh, Noah, thank you. Noah's correct. And Frank, that was the issue that I had there. I wanted you to say the acceleration of Earth's gravity.
Oh,
Not the gravity.
okay.
Okay. So we call this the local acceleration of Earth's gravity. Okay. What do you say we guys, we go ahead and calculate the actual potential energy that I just generated there by way of learning about the units, okay? So for example, if your professor has a mass of 1 kilogram and lifts it to a height of 2 meters, then the potential energy is let's look at the units here. 1 kilogram times 10 meters per second squared times 2 meters. Now, for the purposes of this problem, I'll help you with the math part. 1 times 10 is 10, and 10 times 2 is 20. What I want you guys to do is to tell me what the units are. What are the resulting units of energy?
Joules?
Yes, that's where we're going. It is going to turn out to be the joule, but you first have to give it to me in MKS units here. You have to smush all those together.
Kilograms times meter squared over second squared.
Yes, thank you. Kilograms times a meter squared per second squared. Now, those are the units of energy, kilogram meters squared per second squared. And you can see that that's kind of an abstract quantity to think about. Like, I know what a kilogram is, and I know what a meter and a second are, but when you mix them all together like that, kilogram meter squared per second squared, it gets a little bit confusing to think about this. So as someone suggested a moment ago, this is a good time for us to hide our confusion and for us to invent a new unit of energy known as the joule. We call this 20 joules of energy. Or usually how we abbreviate it is just 20 capital J. Finish copying that down because I'm going to do a whole bit on units of energy now.
So instead of writing kilograms times m square over second square, we just write joules, right?
That's right. That's right. And that's how it's going to work. But I wanted you to be able to see, Juan, that the joules actually referenced some fundamental units of mass, length, and time. And there are many different possible units you can use for energy, Juan. Joules is just it's the sort of go-to standard metric unit. And that's what our next set of notes will be about.
Okay.
I'd like to erase. It kind of looks like some people are writing there. Anyone object to me erasing?
I'm all set, Brendan.
All right, thank you. So let's just reiterate that again, and let's learn about some other common units of energy. This might be interesting to you in your everyday life, okay? So this set of notes will be called units of energy. In the MKS system of units, we define 1 joule as 1 kilogram meters squared per second squared. Most engineers and scientists work in joules. However, there are other units of energy as well. When you pay your electric bill, does anyone know what units of energy you pay for when you pay Narragansett National Grid?
Is it watts?
It's not
Dollars?
Pardon?
Dollars?
Well, in a way, there is a conversion from energy to dollars, right? So that's what you're paying for it in dollars. That's pretty funny. The actual unit that they charge you for, almost, Enrique, it's kilowatt hours. It turns out that watts and kilowatts are a measurement of power. That's another thing I need to teach you today. But when you look at your electric bill next time, it's kilowatts times hours. You need to have the times hours parts there. Today during our homework, you guys will do a problem where we convert joules to kilowatt hours, and that ought to help you understand a little bit better why the hours needs to be there. When you pay for your gas bill, when I look at my gas bill occasionally, I see they're charging me in a unit called therms. And I think that what therms are short for are what we call BTUs. And those are British thermal units. If you went to Job Lot this summer to buy an air conditioner because you were sweating your head off, you probably would have had to look at the side of the air conditioning box to see how many BTUs of energy it could absorb. And that helps you figure out if it's big enough for the room that you're putting it inside of. Today, you're going to learn about the microscopic world of atoms. When we're dealing with atoms, joules are a very clumsy unit that isn't very helpful to use. So you're going to learn about this new unit of energy that's kind of strange. It's called the electron volt. And the electron volt is basically a wicked tiny packet of energy. 1 electron volt is 1.6 times 10 to the minus 19 joules. Put a box around that. That is sure to come in handy today and many other days in our homework. And of course, there's one unit system that we haven't discussed yet, which is our own American imperial system. I don't suppose you guys know what the imperial unit of energy is? I guarantee that you've heard about it before.
Is it calorie?
Exactly, Frank. Now, the official British unit, the calorie, which is a lowercase calorie, is only 4.2 joules. But it turns out that when we use food, when we measure the energy of food calories in the US, food calories are more properly measured in kilocalories. Now, here things are going to get real weird. The FDA did not want to write kilocalories on food packaging, maybe because it might make us sound like those snobby Europeans we're so desperate to distinguish ourselves from. I don't know what the deal was, but they didn't want to print kilo and any kind of metric system on the packaging, probably for political reasons. So they did this horrible thing and they renamed the kilocalorie the calorie, but with a capital C. The capital C calorie, the food calorie, is 4,200 joules. And of course, that leads to a lot of confusion with science students when they get mixed up between calories and calories. Thanks, FDA. Or USDA. I don't know who did that. Some governmental bureaucracy. Let's try an example to see why energy can get easily converted from one form to another. I mean, think about it. You can measure masses floating above the ground in terms of energy. You can measure electricity use in terms of energy, gas use in terms of energy. You can measure the motions of atoms in terms of energy. You can even measure packages of food energy. Let me get an example. So this morning I was late to breakfast, by which I mean I rolled out of bed and I had a hard time stumbling over to the kitchen because that's how life is now. And I considered eating this for breakfast, okay? This is a Trader Joe's dark chocolate peanut and almond bar. Mmm, very tasty. I wonder how many calories are in this thing here. It's not the worst thing ever, but you can see here, let me get my autofocus going. You can probably see here, looks like it's about 200 calories. Oop, right there. Okay, so this thing's packing 200 calories, and I could eat this for breakfast if I was feeling naughty, okay? But it gets me thinking, that's kind of a lot of calories. I could end up regretting that later. And after class, I might start to feel guilt that I indulged in a peanut butter chocolate bar for breakfast. And then I'm going to have to do some exercise to burn those calories off, right? But I'm going to need an exercise regimen that's appropriate for a wimpy physicist such as myself, okay? So I'm thinking that my exercise regimen is going to be, where are we here? We're going to do an exercise that I like to call the 1 kilogram squats, okay? And what I'm going to do is I'm going to take my 1 kilogram test mass and I'm going to put it on the ground. And then I'm going to lift it up 2 meters over my head. And then I'm going to put it down and I'm going to do it again. So suppose I invent a new unit of exercise. And that new unit that we just invented together is known as the kilogram squat, okay? So a kilogram squat is when you lift a single kilogram 2 meters over your head, or 2 meters from the ground. How many joules does it cost to do a 1 kilogram squat, students? How many joules in a 1 kilogram squat? Oh, Lordy, you gentlemen are forgetful today, huh?
1.
Oh, I know. 1.
No, not 1 joule.
Or no.
Look at your notes.
Kilogram.
4,200.
No, that's a calorie. A kilogram squat is when you lift a kilogram 2 meters over the ground. No one can tell me how many joules that is? I mean, this should
Is
be
it
a wicked easy
4.2?
question. Sorry?
4.2?
Nope, 4.2 is the number of joules in a calorie. I'm not looking for the
20.
joule. Huh?
20.
That's right, 20. Because when we did MGH, mass times little g times height, we found that if the height is 2 meters and the mass is 1 kilogram, then that's 20 joules, okay? So to lift a 1 kilogram mass 2 meters into the air, 20 joules. I hope I don't have to do that again because I thought we already did that. Okay, so, you know, a friend of mine likes to refer to these as candy bars. I'm like, no, this is just a nut bar. It's just a granola bar. She says, no, Brendan, that's a candy bar. So let's say a candy bar has 200 calories in it. The question that I want the class to help me solve is, how many kilogram squats do I need to atone for my sins and to burn it off? Is that a question that you guys think you could answer for me?
Is it 10?
It's definitely not 10.
Squats? 10
This is
times
a problem
10.
that requires special techniques.
Oh,
A special technique that I've taught you, Bella, many times. Bella, do you know the technique?
I do, but I keep forgetting the name of it.
What's the name of it? You got to remember the name of it. It's supposed to be very special to you. It's supposed to help you figure out tough things. Come on, guys. Someone's got to, or guys and gals, someone's got to help me here. I'm going to take a seat while I wait for you guys to process.
Joules.
Huh?
Joules.
Joules is not the answer. I need to know how many kilogram squats do I need to do to burn off a 200 calorie candy bar. This is a problem. It's a word problem.
I
And you
could
need
be
a
wrong.
method to solve it.
I could be wrong, but is it 2,000?
No, sir. Okay, look, you can't guess the answer. Guessing doesn't work anymore, students. You have to use the methods that I've trained you in. But I can't actually train you in the methods if you can't remember. What if every time Yoda showed up, Luke Skywalker was like, what the hell's a lightsaber? Then no Jedis would be out there kicking ass across the galaxy, right? You need to remember things. You need to remember the techniques that I train you in. What's the technique that we use to solve tricky word problems?
Dimensional analysis.
Dimensional analysis. Thank you, God. Okay. So can someone please do some dimensional analysis to help me figure out how many kilogram squats I need to do to burn off 200 calories? What's the first step in dimensional analysis? Let's read it off the page together.
Supposed to do 200 cal.
All right, we start with the
And-
number we want to convert. So we'll start,
Yep.
let me erase this stuff below here. Make sure you have that written down. We'll start with 200 calories. That's the first step. So write down the number with the unit that you want to convert. Now what do I do?
The division bar.
Good.
Multiply by division bar. You write your units.
Okay, so let's put in units, Bella.
So cals on the bottom, and I'm gonna say joules on top.
That sounds good. Now let's get the numbers in there. Step 4.
So 1 cal equals 4,200 joules.
Good, because this is a kilocalorie. I was wondering if you were going to mix up lowercase and capital calories, but Bella, you did it right. A food calorie is 4,200 joules. Okay, now what do I do, Bella?
Then division bar again, multiply by division bar again.
Uh-huh.
And joules on the bottom, and I'm gonna say kilo squats on top.
Kilogram squats, or I like kilo
Yeah.
squats. We can call them kilo squats.
Alright,
Okay,
so 20 on the bottom and 1 on top.
very nice. Because 1 kilogram squat is equal to 20 joules. Okay, so Bella, to get the answer, what you have to do is multiply 200 times 4,200 and divide by 20. And what does that give us?
Give me 1 second. I got 42,000. And that would be the kilogram squat. Kilogram squats.
That's pretty annoying, huh? 42,000 squats? Hey, Bella, if you can answer this or if the class can answer this, suppose I could do 1 squat per second. How many hours would it take me?
Hold on. I have to look at my notes for the how many seconds in my hour.
No, you know how many, just do seconds to minutes and minutes to hours. You might not know the number of seconds in an hour, but you certainly know the number of seconds in a minute, don't you? You know the number of minutes in an hour.
Yeah, it's 60 seconds per minute and then 60 minutes per an hour.
Okay, so if you do 1 squat per second, how many hours is that?
Oh, 120?
No.
I think I'm getting it wrong. No, hold on.
At 1
Brendan?
squat, pardon?
11.6 hours. Brendan, the other Brendan said 11.6 hours.
Very good. It would take 12 hours. That's 12 hours of straight exercise. Just for me to burn off 1 little harmless Trader Joe's peanut and almond bar covered and smothered in dark chocolate. I probably shouldn't eat this, huh? It's probably a good thing that I didn't eat this with my morning coffee because I would be paying the price. There's a lot of energy in food, like a lot of energy. That's 12 pure hours of exercise, of jumping up and down. Of course, you burn more energy than 20 joules doing this, right? That's the whole point of jumping jacks. My mass is much greater than 1 kilogram, so we'd have to think about that too. But if I was just a stick figure who lifted up and down a 1 kilogram mass, I'd have to do it for 12 hours at 1 squat per second. It's also interesting how something that started off as lifting a weight above the ground suddenly could transform itself into a candy bar. This is what's cool about energy. It's shape-shifting, it's protean. It can go from a candy bar and transform itself into masses lifting up and down in a gravitational field. What if you guys asked yourself a funky question? Where is the energy? Like, if there's a mass and a height above the ground, the energy is kind of stored in the system of the ground plus the height plus the mass. In some ways, the storing of potential energy in a mass above the ground is very similar to this type of potential energy. You can also store potential energy in a spring, but it's no longer gravitational potential energy. It's electromechanical potential energy. It's the potential energy of all the atoms in this metal lattice wanting to restore themselves to equilibrium. Normally, a spring has an equilibrium position where it's at rest. And in physics, you study springs quite often because they're very instructive for other physical systems. For a spring obeys something Hooke's law. If you stretch a spring, the spring experiences a restoring force that's proportional to the amount you stretch it. So if I stretch it twice as much, I get twice the force pulling it back. If I stretch a spring and hold it there, I've now stored potential energy in all of the coils of the spring because I'm fighting against the spring, and at any point I can release the spring and it snaps back to equilibrium. In some ways, the 1 kilogram mass above the ground is also like the spring, except the spring is invisible because it's gravity. I've held it against the will of gravity, and I can do something with that potential energy, right? I could take that potential energy, I could lift up this mass, and I could carry it over to a small village in Yemen, and I could drop it and release it against some unsuspecting villagers. And well, perhaps that would be a dubious use of my potential energy, but it's one that happens all the time, every day, if you think about it, right? People are constantly releasing potential energy on unsuspecting villagers. These are things we can do with potential energy. Let's talk about another form of potential energy. Let's look at some pictures. Oh, I don't have my slideshow open, but that would be nice if I did. Just a moment here. I wanted to show you a famous picture by the legendary physicist Doc Edgerton. He took a picture which with a strobe light, which could be considered the perfect picture to demonstrate kinetic energy. You can see a bullet having fired from a gun rupturing through an apple here. There is an energy associated with moving objects, and it's known as kinetic energy. Its formula is very simple: 1/2 times the mass of the bullet times the velocity of the bullet squared. And we're going to need to think about kinetic energy a few times during this class, especially when we deal with meteoroid strikes on planets. So introducing another form called kinetic energy. Kinetic energy is the energy associated with a moving object. Usually we define it as the energy needed to take some type of a mass and accelerate it from 0 to hero. Okay, so you have some type of a mass. It could be a BB or a bowling ball, and you fire it out of a cannon at some velocity. And once you do this, you've cost yourself some kinetic energy. 1/2 times the mass times the velocity squared. I wonder how the energy of a bullet compares to the energy of a candy bar. Bullets come in various masses, and they have various velocities. It would be nice to look up a particular rifle, but I don't know enough about. What's the mass of a typical bullet? Depending on the gun, the mass of the bullet ranges between 0.02 and 0.04 kilograms. What about the speed of a bullet? If I was in the services, I might know these questions. They can go from 550 meters per second up to 1,250 meters per second, okay? With a muzzle velocity. So let's just take a peek and let's think about a rifle bullet, okay? If we had a bullet and the mass was 0.03 kilograms, and the velocity was 600 meters per second, I suppose it would have a kinetic energy of 1/2 times 0.03 kilograms times 600 meters per second. Half of 600 is 300. 3 times 3 is 9. And then 2 zeros cancel. Is that 90 joules maybe? All right, let's just calculate it. I'm not feeling that smart today. Oh, squared. Whoops. What are my units here, class? My units?
Joules.
Right. That's a lot more than the energy of a candy bar. I don't know what I'm trying to imply there. Probably something morbid. Okay. Maybe we could think of a more peaceful use of kinetic energy. Oh, here's one. I guess I could use the moving motion of these water molecules to turn this water mill and rotate a turbine and generate some free electricity. Then I could play Nintendo forever and I wouldn't have to pay National Grid. That would be cool if I could do that. There's all kinds of different forms of kinetic and potential energy. Today, I want to teach you guys a little bit about light. Light is a pure form of energy that is not exactly kinetic and not exactly potential. But first, we have to have a discussion. We have to have a discussion about temperature and heat. It's going to turn out that in the next chapter, there's a deep relationship between the temperature of objects and the amount of light they give off. So let's see, I want to do a module on atoms, which will take about 15 minutes, and a module on light. I'm going to just do some very quick notes on temperature and heat. Normally, I do a longer thing about it, but I want to be kind of quick today. So let's just get some notes into our notebooks today. Can I erase students here?
No, wait, sorry. No, wait, sorry.
Just let me know when you're done. Just if that was Juan or whoever that was, just let me know when you're all set.
Okay, I will.
All right. Okay, so there are two concepts that are often confused, and we need to discuss them because they're related to the amount of light that objects give off. There's temperature versus heat, right? And sometimes I ask students to imagine the temperature at which they cook a turkey on Thanksgiving as a starting point. When you cook a Thanksgiving turkey, you might bake it at a temperature of, I don't know, what do you guys cook your turkey at? 350, 400? Sometimes people cook it even lower for longer. Let's say you cook your bird at a temperature of 350 degrees Fahrenheit. Okay? Where's my little red crayon here? I'm going to need that today. When you cook a turkey in an oven, you're cooking it by heating up air and having the air slowly transfer energy to the bird via a process called conduction. And another way that you might go about cooking up turkey is by putting it in a pot of boiling water. That's another possibility, right? Do you guys know the temperature at which water boils in the Fahrenheit system?
Isn't it 1200?
212.
212 degrees Fahrenheit, right. If you could imagine going to rescue or take your turkey out of an oven versus taking your turkey out of a pot of boiling water, most people are willing to quickly put their hands into a 350-degree oven to pull out a turkey, but they'd be a lot more concerned about putting their hands real quick into a 200-degree vat of boiling water to pull out the turkey. Why is it more dangerous to put your hand into a vat of boiling water than it is to put your hand into an oven when the oven is at a higher temperature? What do you think, Jake? If you had to put your hand real quick into a 350-degree oven for 1 second, or your hand into a 212-degree vat of boiling water for 1 second, which would you choose?
Well, I would choose the oven. Like, I mean, I've done this plenty of times, like with baking and stuff.
Right. So why can't you put your hand real quick into the water? I mean, isn't the oven at higher temperature? Won't it burn you more?
Isn't it because like it takes longer because it's heating up the molecules in the air, whereas the water is like already boiling?
Well, the water molecules and the air molecules are both already hot. And I would propose to you, Jake, that the air molecules are at a higher temperature than the water molecules. So that seems confusing to me why it's okay to put your hand in 350-degree air, but not in 200-degree water.
Is it because the water stays on your hand?
But the air stays on your hand. When you put your hand into the air is coating your hand, just like the water is coating your hand.
Does it take longer to conduct the energy from air into us than it does for water?
Yeah, that's the issue. It's a question not of temperature, but of heat. And they're slightly different things. So let's talk, but you had the correct answer, Jake. It takes longer to conduct heat, is how you should have said it, to conduct heat from air to your hand than it does to conduct heat from water to your hand. So let's define.
If I remember right, Brendan, it's the density of the molecules.
Yes, it is the density
transferring the heat. And
yeah,
since you're sticking your hand in the water, it's that heat transfer is
greater.
I'm trying to think of the right word. Yeah, greater. Yeah. And I was trying to remember back to the summer class.
Well, you pretty much said it right. I think the trick is to know when to talk temperature and when to talk heat. Different problems require different things. For instance, the air inside that oven behaves very much like the gas in this slideshow here. The air in the oven is an ideal gas with molecules of air bopping around. These air molecules, in a way, are like a bunch of little bullets, each which can transfer some kinetic energy to your hand. So if you put your hand into the hot oven while you're baking, Jake, those little bullets, can I make them move again? Those little bullets are crashing into your hand. And as they smash into your hand, they transfer energy and momentum. And that is what heat is. Heat is the transfer of energy from the little bullets to your hand. The problem is that in the water, oh wow, that worked out perfectly. The bullets might be moving slower in the water, but there are many more bullets striking your hand per unit time. You get 5 million more bullets hitting your hand per second than in the air. So they can transfer more heat because there are more bullets, even though the temperature is lower. So the right way to think about this is, let's start by defining heat. Heat is simply a transfer of energy. It's a transfer of energy from point A to point B. Point A could be the oven, point B could be your hand. And heat is measured in units of joules, just like any old energy is. When we transfer heat, it turns out there's only 3 methods to transfer energy in nature. And it's called the 3 modes of energy transport. This is like a classic science thing that you should know about. The 3 modes of energy transport are convection, induction, and radiation. Now, as we go forward in this class, at key moments in the class, I'm going to take time to explain to you guys the microscopic details and the differences between convection, conduction, and radiation. But I don't want to tackle that now because it'll be TMI, all right? But you should at least be aware that there are only 3 ways to transfer energy: convection, conduction, and radiation. Let's now define temperature instead. I'm going to go ahead and I'm going to erase my cool drawing here. If I were to define temperature, I would define it in a different way. Temperature it's a measure of the kinetic energy inside of a bunch of particles. So temperature properly defined is the average kinetic energy of a system of particles. And that system of particles could be in a gas or a liquid or a solid or any old thing that you could imagine. The problem with temperature is that we've been measuring temperature longer than we've understood what temperature is, okay? So we've been measuring temperature. You don't need to know this detail. So the idea is, if you really wanted to do temperature right, let's go back to slide 22 for a second. You'd have to look inside your oven and find all of the air molecules, and you'd have to measure the kinetic energy, the speed and the mass of each one of these particles. But that would be an impossible task. One, we can't see the individual molecules that easily. And even if we could, you'll notice that the particles are constantly changing their kinetic energies because they smash into each other and they speed up and they slow down. However, the collection of particles, the ensemble of particles, should maintain an average kinetic energy, because for every particle that collides with one and slows down, another particle should speed up. So the average kinetic energy of all of them added up should stay constant. Rather than try to measure all the individual particles, we usually find something that changes with temperature, and we use that to define temperature. For instance, as you know from glass mercury thermometers, the height of mercury in a tube could be one way to measure temperature. When it's cold, you mark one place on the graduated cylinder. When it's hot, you measure another place on the graduated cylinder, and then you measure the height of the mercury as it moves up and down, as it expands and it contracts. I'm going to erase the heat section here, guys. In our class, we are going to use 3 temperature scales. And I'd like you to take some very quick notes on our 3 temperature scales. I'm going to do this without a ruler because I'm interested in. We have degrees Fahrenheit, degrees Celsius, and for most of our purposes, we'll be using the Kelvin scale. And I'd like you guys to just get down a couple of basic numbers that might be helpful. I'm going to do this kind of quick because I've got a few other modules to do today. So let's do boiling water is 212 degrees Fahrenheit. In the Celsius system, we peg it to 100 degrees Celsius. A human being is around 99 degrees Fahrenheit. In the Celsius system, I believe it's 37 degrees. Room temperature, we set our thermostats to about 68 degrees Fahrenheit in the wintertime. And I think that's around 20 degrees Celsius. And freezing water, (32 degrees Fahrenheit), but in the Celsius scale, we set it to 0 degrees Celsius. Now, these used to be the only two temperature scales in use until people began to realize that temperature is a measure of the average kinetic energy of a system of particles. And what that suggested to us is if we're cooling down a substance, we slow the velocities of all these particles and they get slower and slower, but eventually we should hit some bottom temperature at which all the particles freeze because the temperatures are so low that the particles cease motion. And by freeze, I mean they stop moving. This is well below the freezing point of water, of course. This is the point where the temperature comes to a bottom out. You guys may have heard of this before as absolute zero. Absolute zero occurs at a temperature of -460 degrees Fahrenheit, or here's the key number, -273 degrees Celsius. Now, at some point, Lord Kelvin decided that he liked the Celsius system, but he wanted to reset the 0 point. So Kelvin and Celsius are identical except for one thing. In the Kelvin scale, we start with 0 Kelvin at absolute zero, and we measure up in Celsius degree units from there. So freezing water is 273 Kelvin. The boiling point of water is 373 Kelvin. It's 100 degrees above it. Notice you don't use the degree symbol for Kelvin scale. A human being has a temperature of about 310 Kelvin, and room temperature is about, I don't know, like 293 Kelvin, something like that. So those are some reference temperatures you can keep in mind as we go forward. Okay. We're going to do two more modules. Yes.
I'm not done yet.
All right, Andrew, let me know when
copying.
you're done, buddy.
All right.
You good?
No, I'm still copying. I just need the Kelvin section.
That's fine. That's fine. Go for it. Andrew?
I got it.
All right. It's really important I do two more modules because we need them for our homework. So hold on, guys. My board is getting a little icky here, and that kills your dry erase markers. So I gotta keep it clean, or I'm gonna have to go back to Staples this week. Okay. It turns out light comes from little factories that we call atoms. You guys probably know a few things about atoms, so I'm going to try to keep this efficient, but I'm sure that you don't know everything that I'm about to write down now. Let's start by discussing the so-called Bohr model of the atom. That's the one that looks like a little baby solar system. And we're going to start off with a legendary element that you guys need to be familiar with, helium. Helium is the second most abundant element in the universe. We'll be learning about gas giants. Roughly 30% of the gas giants are made of helium, so it's kind of an important gas. Let's draw a helium atom by starting with 2 protons, which you may have heard are positively charged. And what I'm doing right now is I'm drawing the nucleus of the atom. 2 protons, 2 neutrons, and then 2 electrons orbiting around it. This is a good starting point to learn about atoms. We'll define a few basic terms here. So the little blue pellets, of course, are the electron. The black pellets are the neutrons. The red pellets are the protons. Now, this little doodad in here is the nucleus of the atom. And we refer to protons and neutrons as nucleons, okay? Nucleons are protons or neutrons. In other words, in this atom, helium has 4 nucleons. Atoms, as you know, are the fundamental, indivisible building blocks of matter. In some ways, the Bohr model of the atom looks like a little baby solar system. The electrons are orbiting around the nucleus, similar to the way that Earth and the other planets orbit around the sun. Except these electrons are not orbiting because of the law of gravity. Can you guys guess what fundamental force causes electrons to orbit around the nucleus? What makes an electron orbit around a nucleus? Someone's got to know.
It's energy. I don't
Not
know. I'm
energy.
guessing.
Sorry?
Electromagnetism.
The force of electromagnetism. Let's write that down, okay? Atoms are held together by the force of electromagnetism. This is a new force of nature. Sorry, my spelling got crappy, or my handwriting got bad. It's a new force of nature that has to do with a property called charge. You can see the proton has a positive charge and the electron has a negative charge. There are 2 rules associated with electromagnetism. Rule 1 is like charges repel, and rule number 2 is opposite charges attract. And this makes electromagnetism more complex than gravity, because gravity is strictly an attractive force, whereas electromagnetism has attraction and repulsion. Andrew, let me know when you've got this so I can erase. I kind of have to move quickly, guys.
Got it.
All right, I'm erasing. There's a quick rule of thumb that we need to know about the difference between protons, neutrons, and electrons. So let's make a proton. Let's make a neutron. And let's make an electron. If we compare the particles, if we compare the mass to the charge, we learn that these particles are very different in nature. Now, the mass of an electron is a tiny number. It's 9 times 10 to the 31 kilograms, wicked tiny. But if I define that to be 1 electron mass, I quickly discover that the mass of a neutron is 2,000 times more massive than the electron, and the proton is 2,000 times more massive than the electron. This is one of the reasons why all of the mass of an atom is bound up in the nucleons, because these guys are big fat particles, and an electron is really tiny and wimpy in comparison. But yet the electron has the equal but opposite charge to the proton. An electron has a charge of -1. Neutrons have a charge of 0. And protons have a charge of +1, which is kind of funny because the electron is a wimpy, tiny little particle with its very low mass, and yet its charge is just as strong as the protons, and they balance each other out. Nature's got kind of a weird sense of design in that way. It wasn't very symmetrical. That's one of the fun mysteries of nature, and it's going to turn out this is related to the fact that there are particles of antimatter, which can be generated in nuclear reactions and in particle accelerators. But we'll get to that later. For now, you just have to know some basic facts about protons, neutrons, and electrons. Andy, let me know when you've got that down.
I got it.
Okay. Adam, you good? You need a sec, buddy? All right. You give me a thumbs up when you're ready to go. Sorry, I'm going to have to do some uncomfortably fast notes today. All right, thanks, bud. Okay, I need to define a whole bunch of terms for you. So embrace the suck here because you're just going to learn some vocabulary words. Let's start with a term called the atomic number. The atomic number, which I'll call A, is the number of protons in your atom. The importance about the atomic number is that it defines the atom or element. Atom and element mean the same thing. For instance, if I show you a picture of the periodic table of the elements, I'm sure I've got one of those floating around somewhere. The atomic number is written in the upper left-hand corner. Copper has an atomic number of 29, meaning it has 29 protons in its nucleus. Aluminum has 13 protons in its nucleus. It's important to figure out how you're going to define an atom, because as you remove particles or add particles, it can get a little bit confusing. The mass number I'll call capital M is the number of nucleons in an atom. That is, the mass number is the number of protons plus the number of neutrons in your atom. Mass number is important because the mass number defines the so-called isotope of the atom. What is an isotope? Well, I can explain that very simply. An isotope has the same number of protons but a different number of neutrons. And I'll show you some examples of that in just a minute. Most atoms in nature are electrically neutral. This is the default state that atoms tend to find themselves in. Electrically neutral means the number of protons is equal to the number of electrons. So when you have equal positive and negative charges, your atom has no net charge and it's electrically neutral. However, all the interesting stuff in chemistry comes about because it's possible to either remove electrons from atoms or add electrons to atoms, and that charges them and makes them ionized. So an ionized atom is one in which you remove, or in some funny cases, add electrons to the atom. When you do this, your atoms are no longer neutral, but they have now entered the fourth state of matter called a plasma. A plasma is a charged gas in which ions are floating around with electrons in some kind of gaseous soup. Usually can't have plasmas in the solid or liquid state because you have to raise them to very high temperatures before the electrons will jump off. Okay.
Bring the camera down because I can't see. Dang.
Okay. It's weird. On mine, it cuts off the top, but okay, fine. Atom 1. Andrew, let me know when you've got this.
I'm good.
Okay, I'm really not liking my flow today because I'm kind of just jamming stuff down your throat. Normally we'd play a little game called Let's Build an Atom, which is very helpful, but I don't have time for that today because I need to teach you one more little thing for our homeworks. So unfortunately, the stuff we need to do for homework today is just a teensy bit ahead of us. So I think if you give me just the rest of this lecture here, about the next 10 minutes, I can squeeze in everything you need to know. It won't be pretty, but we'll get it done. Can I erase?
Done.
Good. Okay, today we're going to need a couple of different concepts. One of the concepts we're going to need is something called power. Power is defined as energy per unit time. Power is a measurement of energy flow through a system. The MKS unit of power is called the watt. And watts are defined as 1 joule per second. So 1 watt is 1 joule per second. Usually you can talk about the power of, well, any kind of a system. If a human being uses 2,500 calories per day, that can be measured in watts as well. You have a power requirement, just like a light bulb does. A guitar amplifier might run 300 or 400 watts. A hairdryer might run at 100 watts. That's telling you the amount of energy that flows through the system per time. However, when we deal with light, okay, so in situations where we're dealing with the macroscopic properties of light, let me see if I can just find a picture of a stupid light bulb. When light is flowing through a system, like light is flowing out of this light bulb, energy is streaming out of the filament per unit time. And when we deal with the power of light, we usually give it a new term called luminosity. Luminosity is basically the power of light. So you would talk about the, okay, Frank, catch the video later, okay, buddy? So the units are the same. 1 watt is 1 joule per second. Luminosity is usually defined as the total light output from a star or planet or light bulb. That's one of the concepts that you guys are going to need for your homeworks today. Next time I need to do the inverse square law, but I have one more little bit to teach you here. Let's start by getting this time. Get all this down. Make a note, class. Next time I need to teach you about brightness. But I've got one other thing to do instead besides this. Adam, give me a thumbs when you're ready. All right. One more little module, guys. And after this, we can start our homework. I need to teach you a teensy bit about light today. And let me start by showing you a physics model or picture of light at the beginning of my slideshow here, slide 25. Here's a modern picture of what light is. Light is known as an electromagnetic wave. And it's a form of energy that's created from a varying electric and magnetic field. One part of light is an oscillating electric field. We associate electric fields with static charges like electrons sprayed onto a piece of rubber, otherwise known as saran wrap. And light also has a part of it which is a magnetic field. Magnetic fields are associated with moving charges or with the magnets that you have attached to your fridge. The important thing that we have to do before we start our homeworks today is to say that light has a number of properties which are related to the properties of waves themselves, one of which is wavelength. Wavelength is defined as the distance from crest to crest of your wave. And it's actually a real physical distance that can be measured in meters or in any other unit like inches or feet or whatever. So let's just take this down kind of quickly here. Light is an electromagnetic wave. And that means if one part of it is made up of varying electric field, and one part of it is made up of a magnetic field. Now, what the electric and magnetic field are is a little bit abstract, and I kind of don't have time to explain all that to you right now. But you got to start somewhere, so here's where you're starting. Just know that electric fields are associated with static charge, and magnetic fields are associated with moving charge. All right? Because light is a wave, it has, oh, by the way, normally when I draw light, I can't, it's very difficult unless you are a very talented artist or you have a computer program. You can see that the electric field and the magnetic field are always perpendicular to each other. I've attempted to draw this with my hand, and I found that I'm quite sucky at it. So what normally we do is just draw the electric field and we imagine the magnetic field is there. So usually if I'm going to draw some light, I draw it like this, and I imagine that the magnetic field is hidden there somewhere. So this would be a representation of the electric field. And you can see that it's an oscillating wave. Sometimes when we look at light in microscopic detail, we don't really think about a continuous wave of energy, but we realize that light is made up of these individual particles or packets called photons. Light is comprised of tiny, we could call them packets, or we could call them particles, although they have wave-like structure as well. They're called photons. And photons are to light in the same regard that atoms are to matter. If we say that atoms or matter is made up of individual little nuggets called atoms, light can be considered being made of individual nuggets called photons. Sometimes when we try to draw the photon, we imagine it as a wiggling electric field that has localized spatial dimension. In other words, here's a picture of a photon. You've got a little wiggle, but there's kind of like a little packet that's traveling through space. All right, it has a size associated with it. The properties of photons are the same properties that waves have. And we need to talk about that before we can do our homework today. So I'm really using every minute I've got. Let's talk about the properties of waves. There are many properties of waves, but I want to talk about the three key properties of waves. These are what you need to do your homework today. I got to get rid of this. The three properties of waves are wavelength, frequency, and energy. And each of these properties have their own symbol. The symbol for wavelength is the Greek letter lambda, which kind of looks like a upside down Y or something. The symbol for frequency is a curvy F. And the symbol for energy is usually capital E. The wavelength of light is the actual distance from crest to crest of your wave. And it turns out to be deeply related to color, okay? So the color of light is intimately related to its wavelength. Red has one color, blue has another color. Wavelength is measured in units of meters by default. But sometimes when we're dealing with visible light, we want to measure the wavelength of light in tinier units called nanometers. I don't think you've seen that yet. Where are we here? I was hoping to show you guys a picture of some visible light real quick. There we go. So you'll notice that this is the so-called rainbow or the visible continuous spectrum. Purple is around 400 nanometers and red is around 700 nanometers in the visible continuous spectrum. Each color is related to a unique wavelength. So the units that we sometimes use are the nanometer, which is a billionth of a meter. You're going to need that today. Put a box around that. 1 nanometer is 1 times 10 to the minus 9 meters. Because waves of light travel through space, they have a frequency. And the frequency of light is the number of cycles per second that pass by you. So if I were to make a mark here, like a line, we could count the frequency of this wave by watching how many crests go past per second. So we'll start here, 1001, 1002, 1003, 1004. So basically, one wave travels past that red line every 4 seconds. The frequency is the number of cycles per second that your wave passes by in space. So it's defined as the number of cycles per second of a traveling wave. Unfortunately, cycles or wavelengths are like a conceptual idea. So the real units of frequency are a bit awkward. They are 1 divided by seconds or per seconds. And we introduce a new unit for frequency called the Hertz, after the famous Heinrich Hertz, who investigated radio waves. 1 Hertz is basically another way of saying 1 cycle per second. Lastly, energy usually has units, we've already talked about that today, of joules, or in some cases, we measure the energy of light in electron volts. Now I'm going to give you a little break before our homework, but there's 2 formulas I need to put up on the board for you guys for us to do our work today. This happened in my other class too, so I don't know what it is about this semester. I want to get those formulas up.
I'm not done yet.
Yeah, can you just let me know when you're done, Andrew? I'm sorry.
Yeah.
I got to push today. I had
I
too
know.
This module took a while over the summer too, with the 1020 class.
It does, because our next homework requires like 7 different little things. So it just, this is kind of an irritating part. Normally this is a fun part of the class because I've got cool examples for all of this stuff, but I couldn't afford to today. Oh, by the way, can we have a reminder class There's no lecture on Monday because of a holiday. Isn't that right?
Yes,
Columbus
it's
Day.
Columbus Day.
So we're going to do more on this on Wednesday next week. And then next week, instead of having homework for office hours, we're going to do exam practice problems. Does that sound good? That'll be our last class.
Sounds
before-
great.
I'm gonna have to
I'm
have a-
done.
Thank you. All right, let me just get the formulas on the board so that we can get to break here. Hold on.
That sounds horrible, practicing for the midterm.
Well, it sounds like, does that sound better or worse than not practicing the midterm? Because the midterm's happening, right? Okay.
Oh, I know. I've taken your midterm in 1020. It's a challenge.
Yeah. Two formulas are the speed of light is wavelength times the frequency. Where c is the speed of light 3 times 10 to the 8 meters per second. And the second formula gives us the energy of the photon as a new number called Planck's constant times the frequency. I think there's a C, Planck's constant. And Planck's constant has a value of 7 times 10 to the minus 34 joules times seconds. And these two formulas are the only basic ones you need, but there's a third one, which is a hybrid of these two. And that's that the energy of a photon can also be calculated as Planck's constant times the speed of light divided by wavelength. One of the reasons I had to get this into your board today is we need these three formulas for like 3 of our homework problems. But it didn't make sense to introduce this until I finished all the other modules today, so forgive me. Okay, remember that today our homework is not too long. It's a shorter, it will feel like a shorter homework because the questions are short, but I absolutely need to be done by 3 o'clock. So let's take a 10-minute break. Let's come back at 1:15 and get back to it, okay? I'll see you guys in a little bit. Okay, folks. I only ate half my sandwich, but whatever. We got a job to do here. Let's get going on homework 5. All right, we'll do the usual things to start off our homework. Let's get our name at the top. AS1010 at the top with your section. Whatever your section is. And then this is homework number 5, I believe. Chapter 5. Someone have them questions for me, the numbers?
I got you the numbers, Brendan.
Okay, thanks, Andrew.
44, 53, 54, 55, 57.
Excuse me. I just inhaled some sandwich bits. That wasn't cool. Okay. This homework isn't as bad as the last one, so let's get right to it. Chapter 5, number 44. Andrew, you want to read that one?
Yeah. Let me just see where it is. Is it 44? All right. So, atomic terminology practice 2. A. What are the atomic number and atomic mass number of fluorine atomic atom with
think it's
9
fluorine.
protons and 10
Fluorine.
neutrons. Oh, it's chlorine,
Sorry, fluorine.
fluorine. Atom with 9 protons and 10 neutrons. If we could add a proton to this fluorine nucleus, would the result still be fluorine? What if we add a neutron to the fluorine nucleus? Explain.
Okay, let's start off with the atomic number, A. What would the atomic number be? Let's make sure I've got these questions right.
The atomic number would be 9.
Right. So it's fluorine. Yeah, okay. The atomic number is 9. How about the mass number? What is the mass number, guys?
10.
Sorry, mass number is not just the neutrons, it's the number of nucleons, Jake.
Oh yeah, 19.
18
That's
point. Oh,
So this is 9 protons. Now, the follow-up question said, oops. If we could add a proton to this fluorine nucleus, would the result still be proton? Would the result still be fluorine? What if we added a neutron to the fluorine nucleus? So let's start by adding a proton. Still fluorine, yes or no? If I add a proton to this atom, does it stay fluorine or does it change?
it changed.
That's right. It becomes a new atom, Juan, because the number of protons defines that. And the atom that has 10 protons, sorry?
The number of protons defines the atom that it is, right?
Beautiful. And it turns out the one with 10 protons is neon. No. It would not remain fluorine. But become neon. Atomic number 10. What if we add a neutron? Oh, this is all part A, yeah. Is it still fluorine if I add another neutron?
Yes,
Yes.
because the atomic number stays the same.
But now a new isotope of fluorine called fluorine 20. Fluorine with 20 nucleons. Okay, Andrew, when you're done with that, read us part B.
You said part B?
Yeah.
All right. So the most common isotope of gold has atomic number 79 and atomic mass number 197. How many protons and neutrons does the gold nucleus contain? If the isotope is electrical neutral, how many electrons does it have? If it is triply ionized, how many electrons does it have?
Okay. Start with the number of protons. That should be easy.
$79.
Okay. How about the number of neutrons?
$118.
Very good. You got that by doing 197 minus 79 is 118, right?
Mm-hmm.
Okay. If it's electrically neutral, how many electrons does it have?
If it is electrically neutral, I have to check.
Yeah, what does neutral mean again? It means neutral
Protons,
electromagnetism, right?
protons minus electrons equals 0.
Okay, so how many electrons then, Joel?
79.
Yep. It has the same number of electrons as protons. What about a triply ionized atom? What does a triply ionized gold have in terms of electrons? How many electrons are left?
76.
That's right. I've used the symbol for the electron as E minus. Okay, when you're ready, Andy, part C. I'll just be a floating head until then, sipping some iced tea.
All right. Let's see. Uranium has an atomic number of 92. Its most common isotope is 238U, but the form used in nuclear bombs and nuclear power plants is 235U. How many neutrons are in each of these two isotopes of uranium?
Okay, so the number of neutrons in U-238, how do we figure that one out, guys? How do we figure these things out?
You take out the 92 from the 238 and 235?
All right, let's do it. What's the first one? Don't make me do it.
146.
And in the second one?
143.
Excellent. It's that lower number of neutrons that makes uranium-235 so unstable. Makes it subject to nuclear reactions. That's why they use it in atomic bombs and power plants. There's less neutron glue to hold the atoms together. Okay, 1 down, 4 to go.
Can I please see the bottom part of the board? Thank you.
Let me know when you're done, Juan.
I'm done.
Juan, you want to read us the problem? You down to read 53?
Sure. 53, right?
Yes, 53.
Electric bill. Your electric utility bill probably shows your energy used for the month in units of kilowatts hours.
Kilowatt hours.
A kilowatt hour is defined as the energy used in 1 hour at a rate of 1 kilowatt, which means 1,000 watts. That is 1 kilowatt hour equals 1 kilowatt times an hour. Use this fact to convert 1 kilowatt hour into joules. If your bill says you use 900 kilowatt hours, how much energy do you use in joules?
So we have 2 jobs to do in this problem. When I was foolish enough to let students attempt the homework by themselves, they would almost always try this part of the problem and, due to bad reading comprehension, forget to convert 1 kilowatt hours into joules. However, I'm here and I'm not going to let that happen. So let's start by trying to attack 1 kilowatt hour. It should be convertible into joules. What's the technique we're going to use, guys, to do this?
Dimensional analysis.
Hell yeah. Okay, so let's start with the number that we want to convert and its units. 1 kilowatt times hours. What's the next step?
Multiply by division bar.
Okay. Now here's a hint. The kilowatts are multiplied by the hours, but they're not glued together. The trick in this problem is to deal with the kilowatts and the hours separately. Jake, what do you want to start by dealing with? The kilowatts or the hours?
Kilowatts.
Okay, so what should we convert kilowatts into?
Joules.
You can't do that because kilowatts are units of power, not energy. Joules are energy and kilowatts are power. It might be helpful to know the conversions between these things. So what do we define a watt as from our lecture today?
Energy over time.
I want units.
1 joule per second.
That's right. All right. So that could be helpful. And that could be helpful. Tell me what to do. I'm getting confused.
You convert the kilowatts into watts and then the watts into joules per second.
Great idea, Bella. Show us how it's done. Show these guys how it's done.
So you put your units first, in which kilowatts is on the bottom and watts on top. It should be 1 on the bottom and 1,000 on top.
Yep.
Then times the division bar again.
Yep.
Then you put watts on the bottom and joules per second on top.
Okay. I like your moves, kid.
And then 1 and 1.
And 1 and 1. Right. That's right. So Bella, if I cancel out common terms, what units do I have left now?
You have joules per second
What about that?
times hours.
You have joule hours per second is what you
Oh,
got.
sorry.
Well, or joule seconds times hours. Either way, it's the same. But I would say joule hours per second. So what do I do next then? Because I got to get, they didn't ask me for joule hours per second. They asked me for joules. So,
Dimensional analysis again.
yeah. And what do I do this time?
Then you convert the hours into joule seconds.
Wait, you can't convert hours into joule seconds.
Oh, no.
But I
Hours
can convert hours into what, Bella?
into seconds. Or into minutes, and then minutes into seconds.
Okay, so hours to minutes. And what's my conversions?
1 hour equals at the 1 on the top bottom, 60 on top. 1 on the bottom and 60 on top again.
If I cancel out common terms, what units do I have left, Bella?
Hours per second?
False.
No. Then joule per second. That's the only left.
No.
Because you cross out minutes and minutes, and then you, oh, you can't.
What else can I cross out?
Seconds. But then I'm
What can
missing
I cross out?
hours.
So what units again do I have?
It's just joules.
Which is what I wanted. So go ahead and punch it up for me. How many joules are in 1 kilowatt hour? Come on, folks, time is money. Kilowatt hours are money, as someone mentioned today.
3.6 times 10 to the 6 joules.
Yeah, that sounds right. 3.6 million joules. If you think about it, we just defined a new conversion factor. 1 kilowatt hour is 3.6 million joules. So can anyone think of a faster, more effective method of converting kilowatt hours to joules? Because I can't.
$900 kilowatts per hour per kilowatt hours times 3.6 times 10 to the 6 joules.
Well, let's do it dimensional. Yes, but let's do it dimensional analysis. On the bottom, what am I going to put?
Kilowatts times hours.
Good, the whole thing this time. And on the top, Joel?
Joules.
And then you suggested the 3 million on top, right?
Yes.
3.6 million. Punch them up. Let me know when you got a number. Cam, you're having a rave back there, buddy.
3.2 times 10 to the 9th joules.
I like it. Box that. And that means 2 down, 3 to go. That was pretty quick. I'll give you a sec before I erase that. Cam, are you ready to move on? Cam, you ready? Cam's rocking. All right. Jake, you good? How about Andrew?
I'm good.
All right, I'm erasing. People who watch later on can just pause it, but not so much if you're doing it live. Chapter 554. Jake, you're up. Can you read me a problem?
Yeah. All right.
Camera.
Oh, some part. All right. 54. Radio station. What is the wavelength of a radio photon from an AM radio station that broadcasts at 1120 kilohertz? What is its energy?
They want us to find the wavelength, and they want us to find the energy. Here's a hint. You're going to need those formulas that I taught you today at the end of lecture. Speed of light is wavelength times the frequency. That's equation 1. Equation 2. Energy is Planck's constant times frequency. Equation 3. Energy is Planck's constant times frequency divided by wavelength. They gave us 1120 kilohertz. What kind of a quantity is that, students? What did they give us?
Frequency.
That's a frequency. So which formula do I want? If we want to hit wavelength first.
Number 1.
Hold on a second. What's that?
Number 1.
That's right. But we have to rearrange number 1 to solve for frequency. Anyone know how to do that?
You could pass the h to the other side dividing.
Wait. You're dealing with number 1.
Oh no, that's number 1. Sorry. So you'd pass the Greek letter. I forgot the name of it.
Lambda.
To the other side. Lambda dividing to c.
Good. So you end up with c over lambda. Now, the c is the speed of light, and that's a constant that I gave you before, which is 3 times 10 to the 8 meters per second. Oh, I'm sorry. I just did something stupid. Do you guys see what I did here that was stupid?
Yeah, I was going to say, because you already know F and C's a given, so you should be solving for lambda.
Right. I'm sorry, guys. I got a little confused there. Luckily, the formula is the same if you swap lambda and frequency. Okay, here's my problem. I've got meters per second on top, but my units of frequency are kilohertz. Kilohertz will not cancel with meters per second. So what should I do? Jake, what should I do?
I hate to say it, but is it dimensional analysis?
Yes. Love to say it is what you meant to say. Okay, yeah, of course it's dimensional analysis, Jake, but what are you converting from and to?
Converting from kilohertz
To
photons.
no. I guess the question is, what are the MKS units of frequency, Jake?
Oh, seconds.
Not exactly seconds.
Cycles per second.
Cycles per second, Jake, not the same thing. One is seconds on top, the other is seconds on the bottom. All right, Jake, you're up. What do I do?
Well,
What's step one of dimensional analysis?
write down the number to convert.
So tell me what to write down.
1120
1120 what?
kilohertz.
What's step two?
Times by division bar.
What's step three?
Put in your units.
All right. So what units need to go on the bottom? You should at
So
least
kilohertz.
kilohertz. What do you want to convert into?
Cycles square or cycle per square. What?
Maybe you should just convert to hertz first.
Okay. That sounds good.
Let's get rid of the kilo before we start messing around, all right? What do you think the conversion is from kilohertz to hertz, Jake? I bet you've got no idea what a kilo means, huh?
Is it 1000?
Yeah, where does the 1,000 go?
1000 goes on the bottom. Top.
Yeah. One kilo is 1,000 of something else, right?
Yes, yeah.
All right. So 1 kilohertz is 1,000 hertz. Okay, so what's the conversion from hertz to cycles per second?
Isn't it 1 hertz equals one cycle per second?
Right. So as soon as we multiply 1,000, we're done. And that gives us 1.12 times 10 to what power?
Six.
Six.
And that's what we'll plug into our formula then. So the wavelength is 3 times 10 to the 8 meters per second divided by 1.12 million hertz. What does that give us?
Gam's rocking out, or somebody is.
Yeah, some trance music. Oons, oons, oons. Let's get through this.
Look for my calculator.
Punch her up.
250.
Doesn't it round up to 260 actually? Do I have to do this?
I got
If I have to,
268.
I got 267.857.
That's what I got.
oh,
I got
That's
so,
exactly what I got too.
I got it wrong. Sorry.
So
so 270.
268,
Oh,
270, yeah.
man, I almost knocked this computer right the hell off this. I almost did a very bad there. All right, here we go. Getting too old for this shit. What are my units? Good. I like it, Cam. What are my units?
I know, but I'll let them try to figure it out.
Jake, Cam, Larson?
Joules.
No. You got meters per second divided by per seconds.
Kilohertz?
Oh,
Meters.
seconds.
Meters. That's a pretty long photon, right? How many meters is a football field? I certainly don't know. I guess if I ask the meters, they're going to
Well,
give
it's
me
100 yards, so it's meters slightly longer than a yard.
Yeah. That's
Or
basically
yards slightly.
three football fields, right? A single radio wave is 3 football fields worth of fun. We also have to get the energy. Which formula do I want for that? Number 2. I've got to erase everything. Can I erase?
Go right ahead.
Yeah.
I'm all set.
So the energy is Planck's constant times the frequency. We don't really need to do much because we already converted the frequency. So Planck's constant is 7 times 10 to the minus 34 joules times second. And the frequency was 1.12 million hertz. So punch them up and tell me my energy. Shout a number at me.
Hmm.
2 sig figs.
I don't know if this is the right number.
Just shout it at me.
Yeah.
Yeah,
I got 7.84 to the negative 28.
Yeah, that's right. Yeah, that's what I got too. 7.84 times 10 to the 28.
Wait, positive or negative 28?
Negative.
Oh, negative 28.
Units?
Joules.
Good.
Joules, because it's for energy, right?
Exactly. And because seconds cancels with per seconds. All right, that's 3 down, 2 to go. We're cruising, guys. We are cruising. Cam, you want to read a problem?
Sure, since I already have it on my phone.
Cool. Wait, hold on. Before can I erase, guys? All right, I'm erasing. I'll leave those formulas up in case we need them. Okay, Cam, read us 55.
Problem 55. Okay. UV photon. What is the energy in joules of an ultraviolet photon with wavelength of 120 nm?
Nanometers.
And what is the wavelength of an X-ray photon?
Wait a minute. I think you skipped something. UV photon wavelength 120 nanometers. First, they asked for their energy, and then.
Oh, it asks what is its frequency. My bad.
That's okay. So we've been given a wavelength of 120 nanometers. We got to get the energy and the frequency. Here's a hint, guys. We can't use any of these formulas until we convert nanometers to meters. Cam, your job is to help me convert nanometers to meters using dimensional analysis. I just got you started. 120 nanometers. Now what do I do?
Just write it down.
Yep. So we got to convert this, Cam, to meters.
Okay.
So tell me how to do that.
Let's see.
Let's use your steps of dimensional analysis, Cam. What's the first step?
Thinking.
Just don't think. Read it off your notes. Read your
Oh.
dimensional analysis for me. You don't want to think. You want to just do the rules. Just do the rules.
Okay, so C equals.
No.
Oh.
I want you to go to like the first day of class notes and find the
Okay.
step 3 stars next to it. And I want you to read me the 4 steps of dimensional analysis. See, I can't do this for you with the test. So you have to know how to find the info to solve it. Just read the
Right.
4 steps and follow the 4 steps. It's so easy.
I'm trying to find the steps on my notebook.
I asked you to put 3 big stars next to it so you'd be able to find it. It should be on your first or second or third page, one of those 3.
All right.
It will say 4 steps of dimensional analysis. There'll be 3 stars next to it.
I got him.
Well, let's let Cam find it. Cam, you were there that day, right?
I believe so. I was here for every class. I'm trying to find which. I'm a little lost on my notebook.
Shit, can you put your camera on your notebook? This is impossible. You got to be able to. What the hell is the point of having a notebook if you can't find things? Cam, show me your notebook.
All right. I'm not sure how to do that.
Just hold it up to the camera.
Cam, what are the steps to convert?
Hold on, just
units?
hold up. Yeah.
He's thinking too much.
Yeah, I am thinking a little.
No.
I think I might be going a little overboard.
You shouldn't be thinking at all. You should just be looking for the 4 steps of dimensional analysis. Can someone else tell me what? See, I'm not taking notes.
Yeah,
Tell me
someone
what
help me,
page it's
please.
on. Wait, Juan, did you say you had them?
Yeah.
What page is it on in your notes?
Page 3.
Page 3. What comes just before it? Like, tell me some stuff that's around that so Cam can find it in his book.
I see ecliptic definition 1, 2, then C.
You see the definition of ecliptic, Cam?
I remember that day, but I'm trying to figure out which. Oh, I think I found it.
4 steps of
Path of the
dimensional
sun.
analysis, right?
Uh-huh.
All right,
Pass
what's
of
the
Earth around the sun.
But go below that to the 4 steps of dimensional analysis.
Okay.
Did you write that down?
I wrote down pretty much everything.
I just want to read the 4 steps of dimensional analysis so I don't have to kill myself.
I'm sorry.
Yeah, that's all right. Okay, Greg's going to help you out, Cam.
All
Greg-
right, I'm a little off.
Greg, what is the first step of dimensional? But you're doing this, Cam. Greg's just going to read you the steps.
Okay.
Greg, what is the first step of dimensional analysis?
Well, times the division bar after you have your
That's
number
step
down.
2. I don't want anyone getting creative
Oh.
here. I want you to follow the goddamn rules. First step of dimensional analysis. What is it?
Get the number down that you want to convert.
Oh, I found it.
All right.
Write
good.
down the number to convert with its units.
Bam. I did that.
Bam,
for you,
there's the
Cam.
number.
You don't realize it,
And
but I
then
already did step 1. What's step 2, Cam?
Multiply by a division bar.
What's step 3, Cam?
Put units in first to cancel.
Give me some units.
I believe the units is one of them is kilometers.
No. You've got nanometers and you're trying to get to meters.
Okay. Sizes, degrees.
No.
AU.
Stop.
Oh.
Slow down. Cam. Whatever unit you have up here, you always put the second down there. So what unit do I put down here?
Trying to look.
You don't look for anything.
I'm looking on my notebook.
I know. I want you to stop doing that. Turn off the
Okay.
computer, Luke. Now it's time to use the force, okay? Look,
Okay.
what are you trying to convert from and to, Cam?
Meters, right?
That's what you want to get to, and where are you coming from?
Degrees.
No, you do not have degrees. What do you have? Cam, it's here. Follow my finger.
Oh, and M.
NM. So those are the units that should be here. Tell me which one's on top and which one's on bottom.
NM goes below.
Nanometers on the bottom.
Yeah, nanometers go in the bottom and meters go on top.
All right. Now you've got to look in today's notes to find a conversion factor from nanometers to meters. So go back to today's notes.
Okay.
At the end of class, I gave you that conversion. Look under the properties of waves, wavelength, and there you will find your conversion factor.
Properties.
Sometimes I feel like teaching is like, it's like when you go into Savers and they've got a rack of puzzles and you just know that every single one of those fucking puzzles is missing a piece somewhere. So each one of you are missing a piece, and I just don't know which piece each one of you are missing. It's very difficult to know before you open the box which pieces are missing. So my job is to help you find those missing pieces and make a whole puzzle again. So Cam, what I want you to do is go to the properties of waves and find the conversion factor between nanometers and meters.
Okay, so let me see. Okay, I found a page. Let's see which.
Look under wavelength. I wonder.
Okay.
If I was in the class with you right now, I would go to your notebook and point it out for you. I don't know if your handwriting is just shit.
1 times 10 to the negative 9.
All right, where does that go, Cam? You got to tell me whether it's top or bottom.
That goes to the top.
Yes, and what goes on the bottom?
1.
That's right. Okay, now watch this, Cam.
Okay.
120 times 1 is what?
120.
And so you get 120 times 10 to the minus 9 meters. Holy jumping Jesus. Cam, we need to practice on dimensional analysis, okay?
Yeah, I also got to figure out where I write everything down in my notebook too.
Well, that's a skill that comes with time. So you're only at the 101 stage now. You'll get better at it. I'm not good at that myself. Okay. So which formula do I want now? I've got a wavelength. I want the energy. What's my best formula?
The second one.
That requires the frequency. We don't have that yet.
Oh, there one.
3.
Yeah, because that will go right from wavelength to energy. So we'll do energy, Planck's constant times the speed of light divided by the wavelength. Planck's constant is 7 times 10 to the negative 34 joule seconds times 3 times 10 to the 8 meters per second divided by our wavelength, 120 nanometers. Punch them up.
120 times 10 to the negative 9 meters.
Correct. Oh, did I say?
You said nanometers.
Oh, 120 nanometers. 10 to the minus 9 is nano.
Yeah.
To me, nano and 10 to the minus 9 are the same thing, Joel.
I know, but you're not using the correct term.
Did I say 120 times 10 to the minus 9 nanometers? Or did I say 120 nanometers?
But we have meters on top, so you have to keep your.
Okay, fine. Whatever.
Yeah.
Yes.
Otherwise you get confused.
Fair.
I don't know if I punched that in right, but I got a weird number.
Just read your weird number.
I got 1.75 to the power of -18.
That's what I got.
Okay, so 1.8.
To the -18.
Hello?
Yeah, okay. What are the units?
The units would be meters or nanometers.
Meters cancels with meters.
Okay.
Is it seconds?
Joules.
Joules.
Seconds got canceled. Never mind.
Joules.
You're solving for E. Answer has to be in joules.
All right. Now we want to find the frequency. Which formula should I use for the frequency?
2.
We could use 2 and plug in our energy.
Oh, 1. Actually, 1.
Yeah, 1's probably better because then we can plug in the wavelength. So frequency is the speed of light over the wavelength. The speed of light is 3 times 10 to the 8 meters per second. Over 120 nanometers, or 120 times 10 to the -9 meters. However you like it. But you're right, Joel. I shouldn't be confusing these pups.
I got 2.5 to the 15th power.
What are the units? By the way, say 2.5 times 10 to the 15th.
Okay. Units would be seconds.
Nope. Meters do cancel with meters, though. But your answer isn't seconds, Jake. Cycles per seconds is Matt, or 1 over seconds, or 2.5 times 10 to the 15 hertz. Okay, write them up. One last problem to go. And then I'm done, and I can go home. All right.
During this problem, my computer died, and it forced me to leave the Zoom meeting, but I was able to join back.
Oh, okay. Did you miss much, or just write all that down?
No, I took a picture just to write it all down.
All right, cool. That's great.
I
How about
took
the
a
rest
picture.
of you? Andrew, are you still writing?
I'm all done.
All right. Joel, you good?
Yeah, I'm good. I'm just
Racing
starting
now.
on 57.
All right. Joel, can you read us 57?
Sure. How many photons? Suppose that all the energy from a 100-watt light bulb came in the form of photons with wavelength 600 nanometers. Note, in reality, light bulbs distribute energy over many wavelengths. See exercise 51. Part A, calculate the energy of a single photon with a wavelength of 600 nanometers.
So 600 nanometers corresponds to orange. Although I used red because the orange is kind of faint. Our first job, A, is just to find the energy of one photon whose wavelength is 600 nanometers. Cam, Could you
Yeah.
help me convert 600 nanometers to meters?
Lost again.
Walk me through the conversion from 600 nanometers to meters.
Okay, so so they do 600 nanometers
Good.
times 1 times 10 to the 9th power.
Let's do the units first, Cam. You got to put your units in first.
Oh, nanometers would go below and meters would go on top.
Okay. Now give me the numbers.
Okay, so for meters, it'd be 1 times 10 to the 9th power.
-9.
-9. That's, I didn't put negative.
It's very important. What goes
Yep,
at the
and
bottom?
then below 1.
All right. And can you do that in your head? How did we do that before?
It would be 600 times 10 to the -9th power.
Excellent. Okay, class. Now we need a formula to convert this, or to calculate the energy of the photon based on its wavelength. What formula is that?
Planck's constant. E equals h times f.
No. We do not have the frequency, Joel. Try again.
It would be 3.
Yeah. Planck's constant.
H times C over, I forgot what unit that is.
Lambda. Just call it wavelength.
Wavelength, okay.
So Planck's constant is 7 times 10 to the minus 34 joule seconds times the speed of light, 3 times 10 to the 8 meters per second, divided by 600 times 10 to the minus 9 meters. Put you up.
I got 3.5 times 10 to the -19. I mean, negative. Units. Joules.
Good. That's part A, done. Take a second to get that down, and then we'll go to part B. Okay, I'm erasing.
Oh, I need the answer. Thank you.
Okay. Joel, how about part B?
All right. How many 600 nanometer photons would have to be emitted each second to account for all the light from this 100-watt light bulb?
In other words, they need to know the number of photons per second that are leaving the bulb. How in blasted Jesus are we going to do that? How could I possibly? I know that the energy of a photon is 3.5 times 10 to the negative 19 joules, but that's just one little photon, right? I do know that there's 100 watts of energy streaming out per second. I wonder if I could mix those together in some ways as to get photons per second. Let's start with 100 watts. How does watts relate to joules?
One watt equals 1 joule per second.
So 100 watts equals 100 joules per second. Can someone think of a way to go from joules per second to photons per second? Can you think of a dimensional analysis way to do this? Let's use dimensional analysis to find the number of photons per second. What do I do?
You write down the number to convert with its units.
Did that.
Then you multiply by the division bar.
Okay, I like the way you think, Juan. And now what?
And then you put units and the first to cancel.
So
you put like, and then you cancel.
What units do I want?
You want joules over seconds at the bottom.
No. Right. I want to end up with photons per second.
Oh.
So I already have the per second. Why don't you leave the per second alone?
Okay, so then you just do joules at the bottom.
And what do you want on the top?
Could be wrong, but seconds.
That's wrong. Then you'll end up with joules per joules, which is nothing.
Which is not, okay.
What are you trying to get?
I'm trying to get photons.
Per second. So if you have joules cancel out, what do you want to go on top?
Oh.
Photons.
Huh. Now what's step 4, Juan?
Step 4 is put numbers in second using conversion factors.
If only you had a conversion factor from joules to photons, then you'd be set. Where would you find such a thing? How do I find a conversion factor from joules to photons?
The notes, right?
These aren't any old photons. These are 600 nanometer photons.
Okay. So you got me, because now, I don't know.
This is a tricky part.
Yep.
I want to see if one of you guys can think your way through it here. What do I do?
Wait.
Let me check my summer notes.
Convert the nanometer to meter, maybe?
We already did that. You're not looking for nanometers to meters, you're looking for joules to photons. In other words, you need to know how many joules are in a photon. You know, when I was a kid, there was this guy on Sesame Street. I feel like him right now. He's the guy, he would do this. He'd
Oscar the Grouch.
I can't find a word to rhyme with snow. I must have a lyric.
This guy, I think they took him off Sesame Street. This is what he would do when he couldn't get it right. He would do this.
I do a rhyme all the time. One that, they run all the time. They run.
He'd bang his head on the piano. He'd say, "Oh, I'll never get it right," and then he'd smash his head on the piano. I think they took this guy off it because it probably wasn't a good role model for kids. But now every time I get confused, I think, "Oh, I'll never get it right." Dong.
That's exactly how I felt on the last problem.
That's okay. That's okay. I understand. This is what physics and astronomy does to you. It makes you feel like that constantly. It
Do
constantly
we
makes
actually
you
have like photon in the notes?
It's not about the notes, Jake. It's about these particular 600 nanometer photons. This is a conversion from photons to joules, which suggests how many joules are in a photon, which might be something you've already done and didn't realize it.
Is that six?
Is that 100?
No, that's not 600 nanometers, is it?
No.
Is that 100 watts or no?
At the speed of light?
No.
You got
What did you do in part A? What'd you do in part A?
That's not E. That's not the joules, is it? 3.5 times 10 to the negative 19 joules.
Well, what is this E? What is this energy? It's the number of joules in what?
Joules.
One
And a
photon.
In one photon. So it's the number of joules per one photon, right?
So it's 3.5 10 to the negative 19
Where? Where does that go?
at the top,
No.
at the bottom then.
One photon is equal to 3.5 times 10 to the minus.
Oh yeah, because it has the joules at the end. Never mind. I got it.
Okay, punch them up. One sig fig is fine. I really wanted to see that Sesame Street guy smash his head on the piano, but I don't know, maybe they he would just go, "I'll never get it right."
I got 2.857, which we could run up and go to 2.9
Or even 3.
or even okay.
3
And
times
then
10 to what?
power of 20.
Don't forget about the power one. That's the part that matters.
Power of 20.
Yeah.
Power of negative 18. Oh, never mind.
What are the units?
Photons.
Not photons, but
Per second.
Per
photons
second.
per second, which is what they asked for. Juan, I'm going to give you a hint for the exam, okay? This is not your number. This is your number, okay? That's the part that matters. Okay, what's part C say, Joel?
Based on your answer to part B, explain why we don't notice the particle nature of light in our everyday lives.
In other words, why can't we see one photon? Do you guys know why we can't see a single photon coming out of a light bulb?
They're so small.
Let's talk about that. Small.
Because there's too many damn photons per second.
Let's try that one. Too many. All right, we have 2 different suggestions. Now, I think you said small, Jake, because 600 nanometers is small, correct? But Jake, here's the problem with that. The color orange is all 600 nanometer light. So if 600 nanometers was too small to see, we wouldn't be able to see the color orange. So that's not good. Too many? There's too many of all kinds of things, Joel. If you go to the beach, oh, Matt says the speed. There are too many grains of sand on the beach, but you can still see individual grains of sand. Matt said because they're too fast. That's also wrong. Matt, I agree that the speed of light is pretty fast at 3 times 10 to the 8 meters per second. The problem is, Matt, that all light travels at 3 times 10 to the 8 meters per second. If light was too fast to see, you wouldn't see any light. This light travels at 3 times 10 to the 8 meters per second. It can't be that light is too fast to see, otherwise you wouldn't be able to see light. They all travel at the same speed. What could be another reason, another physical property that describes why I can't see one photon? It's not about size, it's not about speed, it's not about number.
Is it because it's gaseous?
No, photons are not gas. They're not matter.
Well, it was worth a try.
It was worth a try.
Maybe it's got something to do with that.
The energy.
Yeah, that's a really, really small amount
Is-
of energy.
So small.
You need a certain threshold of energy for your eye to register and detect the hit. And if you only pump out 1 photon per second, that's 10 to the minus 19 watts. That's not bright enough to see. The answer to why you can't see 1 photon is there is not enough energy in 1 photon for your eye to detect it. It's about energy, not about speed or size or number. Well, holy-
Exactly what we said.
Right. Yeah, kind of. Okay. So guys, we finished homework number 5. And that means I get a half an hour.
Oh, Brendan, can you go down? Because I can't see the rest of the board.
Sure thing, bud.
All right, thank you.
All right, time to take some pictures of my notebook and send it.
Yeah, take those pictures and send them in. Anything else we need to talk about? So no class on Monday, right? If you're in the night class and you're still watching this, I probably need to get in touch with you so that we can have a chat about how we want to do the
Thank you.
You got it. So I'll probably be in touch with the night class particularly because they might be taking the exam at night. We're going to be taking the exam during the day. So Wednesday will be our next Wednesday, a week from today, will be our last class before the exam. Hey, I don't have this wrong. There is a holiday on Monday, right? Did I get
Yes.
that right?
Yes.
Okay.
Yes, there is. Columbus Day.
Okay. Although I don't know if, yeah, okay. So, so on Wednesday, we'll do a little more work. We'll talk about the exam, and instead of homework session, we'll do practice problems. Okay, guys, I'm gonna go because I got this meeting to get ready for, so I'll catch you guys later,
See
all
ya.
right? All right, bye.